Next up, we have a great keynote address from industrial AI expert, Dr. Chetan Gupta, who's here with us from Hitachi. At Hitachi, Dr. Chetan Gupta heads the Industrial AI Lab. Hitachi Global Insights Lab, and also co-leads the Global AI Excellence Center of Excellence. He's built one of the strongest teams in industrial AI, ground up, consisting of data scientists, architects, and developers. He's passionate about building industrial AI systems for manufacturing, mining, and energy management systems are some of his passions. Dr. Gupta also has over 100 papers and patents included in a whole range of areas. He got his PhD in mathematics and master's in mathematical computer science and chemical engineering from the University of Illinois at Chicago. So let's welcome Dr. Chetan Gupta and give him a big round of applause for his talk.
Thank you. So I have the unenviable task of keeping you awake after lunch. Please help me. So let's get started. So I'm going to give sort of a talk from a practitioner's viewpoint today. Mostly talk about use cases, my experiences working in the field in research industrial AI. I'll leave some of the technical details out, and if you're interested in those or specifics of algorithms or something, please reach out to me after the talk. Okay? This should work like this.
Yeah, it should work. Just take it.
Okay, so as this is going on, I'm going to ask you, this is a good wake-up exercise. So if you look at this, what's common to all of these? I have not yet received an answer in any conference I've given. Let's see if this is different. And think about the fact that I'm from Hitachi, and Fung cannot answer. So, so what's common to all of these is they all contain a motor, right? That wouldn't have occurred to you. So motors are ubiquitous everywhere, right? Your car seat has 8 motors. Your car, for example, your car has 40 motors, over 40 motors. You would never have thought about it. They work so seamlessly that you don't think about it, right? And that's what my vision of industrial AI is. That industrial AI will be everywhere, but it'll work so seamlessly that you won't even realize that AI is working in those things. And that is the challenge, right? How do I get from where AI is today, where I can't trust it often, it's not very reliable, to the point where I have enough trust in it so that it's everywhere and you don't notice it, right? So that's sort of the wake-up sort of a slide, all right? So let's get to more technical matters. I think I will use, yeah. So several years ago when we started the Industrial AI Lab, I don't know whether the Industrial AI term was coined by then or whatever, but so we came up our own definition. So which is application of AI, machine learning, and related technologies towards addressing real-world challenges in the societal domains. And the idea at that time was to not focus on any particular vertical, right? So I'm not going to do AI for manufacturing or AI for fleets or energy systems, but look at these different industries or societal domains and see what are the common problems, right? So what is it that I can learn by looking at these? And so one thing that sort of jumped out after working in this space for several years is there are major functional areas. And you could develop solutions in these functional areas that could be horizontal, but applied to multiple different verticals. And these should not surprise you, right? So maintain, repair, optimization, operations optimization, supply chain management, quality and safety, and automation and robotics, right? And from a robotics perspective, I sort of want to focus more on not a robot per se, not a robot control, but how do I manage multiple robots in a factory setting or in a mine setting, okay? But the question is, why should we do this, right? So besides the fact that I want to do it, Hitachi has to pay me to do it, and I have to justify to them why they should pay me to do that, right? So it turns out that industrial AI has a lot of benefits, right, as you can imagine. And it's good to think about 2 classes of people who benefit from industrial AI, and that helps you think in terms of what problem you should solve, what use case you should go after. So one category would be operators, right? So for example, if you're running a fleet of vehicles, then you have a different concern versus whether you are OEM, you're making something, you're a factory or you're a power plant. And for both categories of users, there are different benefits. And it's very important to tie the problem that you're trying to solve with a business benefit. Otherwise, no one will give you money. And I think that is an important thing to think about. That's how you make a positive change, a positive impact with your technology. So in terms of operators, operational efficiency, as you can imagine, extending life of equipment, increasing uptime reliability, operational costs, and so forth. And from an OEM perspective, you have design improvement. And very often what interests them is number 3, was new value-added IoT services, because this increases the top line and genuine parts and upsales. So to convince you that there is something called industrial AI, I'm going to look at 2 very different industries and show you the commonalities between them. So what you see here is an open pit mine. So open pit mine is where you blast rock surfaces and then you extract the ore. You pick up the ore using large shovels, and then you either separate into waste material or the ore that you're interested in. Right? This is the largest mine in Australia. And to give you this context of how large this is, the tiny dots that you don't see are these trucks, mining trucks. And a typical mining truck is 3 to 5 story tall building. Right? So that's how big they are. So this is the scale of the environmental destruction as well. But besides that, this is the scale of the mine. Right? So if you're trying to operate this mine, what people try to do is, they call it pit to port optimization. Right? So I want to, from the pit to the time my ore goes to the port, I want to optimize everything. So things that you have to worry about are things around shovel starvation, meaning I have blasted rock surface, I am ready to pick up something, but there's no truck. Otherwise, your truck are queuing up, and as they're queuing up, they're not being productive. You think about demand forecasting as to what I should produce, which grade I should produce, and then I have to schedule my drop-off from the time I've prepared my ore to the trains that will carry it to the port, that will carry it to the customer. Right? So these are the sort of problems you're thinking of in an open pit mine. Now, if you look at manufacturing, this is a manufacturing plant, this is from Hitachi, and this is making, if I remember correctly, they're making mining equipment. Okay? Now again, very same problems of resource allocation, about how much should I produce, how should I optimize my end-to-end operations in a factory. The one problem I didn't discuss earlier is around operator profiling. Different operators do different things well. So how do I assign them to different tasks? How do I upskill them, upgrade the skill level? So what I wanted to show with these 2 examples is that looking sort of, if you take a step back, mining and manufacturing, which sound very different industries, have a lot of common problems. And this leads to this taxonomy that we have built inside Hitachi. Oh. Okay, or I can hold this in my hand.
Online folks can hear it.
Okay, all right. So this brings me a taxonomy that is partially shown here because of lack of real estate. But of the 5 verticals that I pointed out earlier, horizontals rather, maintenance, repair, operations, and quality, these are the set of canonical problems that we have come across as we've worked with multiple customers. Right? And so in terms of estimation diagnostics, prognostics, or evaluation recommendation. And my belief, having worked with a very large number of customers, having talked to a very large number of executives, is that if you were to solve these problems in a systematic way, in a way that they can be then repurposed for different customers, you would have solved 80% of the problems in industrial AI. Okay? So this is sort of our sort of guiding light in some sense. So this is sort of the problem. Let's sort of switch to what kind of data that we see in the industrial AI. This would not be a surprise to you. But I think what is interesting in industrial setting, we have seen all kinds of data. Event data, sensor data, maintenance records, operational data, natural language data, image data, and acoustic data. And one of the reasons I put it up here is to, when you compare this with, suppose you were to go to a AI conference, which I stopped going anymore because I can't relate to that as much. Because my problems are very different, very practical. But the data types are very different, right? I have to think about sensor data. Because if I just look at the image, that is only going to give me the surface information about a particular equipment or an operation. How do I learn what's happening inside it, right? I have to look at event data, maintenance records, operational data, right? So the AI that I need to do has often to be multimodal, okay? I have multimodal data. The other point I want to make is, this is sort of, when we think about AI-based systems, these are the different sort of, you can go from decision support system to monitoring systems, recommendation systems, and automated systems. I think Christopher brought up the example of autonomous driving. So we believe in industrial setting, we are still not ready to go to completely automated systems. So very often our solutions end at recommendation systems because the amount of confidence that we have in the output, where the cost of making a mistake is very, very high, right? People can lose their lives. You can't trust AI to build completely autonomous systems unless the context is very, very limited. So, for example, in the autonomous driving use case, we have been trying to do autonomous driving now for some time. A lot of billions of dollars have been invested in that space, and we can't do autonomous driving in a city, for example, today. But Hitachi has a program doing autonomous driving in a mine. So why is one feasible, the other one is not? Because in a mine, my environment is quite controlled, right? There are not stray people coming into the mine, and I can model the mine very well. So the important point is, unless I can have very controlled environments, I'm not comfortable deploying completely automated systems. And very often the value is in making a recommendation to a human who can sort of vouch for the safety of the result. The other point I want to make about AI systems, if you think about an enterprise and the scale of decision making, right? There are control decisions that we all understand, right? So control logic, I'm running a machine, I need to control. Then there are operational decisions that takes minutes or days, and the strategic decisions, what is the long-term strategy for a company? And if you think from this perspective, then typically AI ML is deployed in the operations part today. We are not reliable enough to do control, and we are not smart enough to do strategy in some sense, right? So our sweet spot is operations. So think about operational decision making as the sweet spot for industrial applications of AI, okay? And that's where you can involve a human, and that's where you can have a lot of gain. So I'll try to motivate through some use cases and to sort of show you different flavors of things that we have done. So, and each of them will have a different flavor of a slide because I borrowed from several slide sets to do this, right? So, repair recommendation, right? So this was very interesting. We work in the largest fleet company in the world, and we wanted to tell them failure prediction. Because everyone was selling failure prediction, we said, we can do failure prediction. They said, our problem is not failure prediction. Our problem is that our technicians are retiring, they're getting old, and when the vehicles come in for repair, we don't know what to do. So the younger technicians will do two things. They will either take a lot of time to decide how to repair a vehicle, or they will do something, the vehicle will go on the road and come back within 60 days. So it's a wasted effort, right? So they wanted to make an AI-based system that helps them recommend what is the right repair to do. And it turns out that this problem is really very useful to them. Now it's been deployed for the last 3 years. The type of input that we had was event data. So for people who drive a car, there is an OBD dongle at the bottom where the technician typically inserts a dongle and downloads the fault codes. So a very similar protocol exists in trucks as well. So you have event data, and the event data is very interesting and ties very much with the flavor of the conference today, because event data is incorporating domain knowledge, right? So event data is defined over whatever underlying sensing that you have by people who build that system. But event data often is very noisy, and it is built in a context that is devoid of operations, right? So people build these things in factories, they test them in a factory setting. So when you operate these vehicles or these equipment, any equipment, the event data can be misleading. So you need to marry the event data with all kinds of other data to get a useful sort of model out of it. So you had to marry the event data with the historical maintenance records, make, model of the vehicle, and also the verbal complaint, right? So the operator is saying, look, this is what I hear, or this is what I see. So can you use that as well as the event data to build a model that can then say, okay, this is the right repair to do. The interesting insight here for us was that we didn't try to do root cause analysis. Right? We said the root cause analysis is helpful, but if you have to repair, it's more important to know how to fix it. And my belief is this is how very much doctors work today. They really don't know what's causing your illness, but they'll give you a medicine, and that will work. And this was the instinct that we brought to the problem. And it really helped solve this problem. It's been very, very, very useful to them over the last several years. So once we had done the repair recommendation, we went and did failure prediction. And this failure prediction was in terms of number of miles to failure. I'll come back to this example in the end when I talk about challenges. But what was interesting to me is, as I've spoken to a lot of other people in the industry, very often folks who are serious about deploying models, they want to do a recommendation system first before a prediction system. And it turns out because the recommendation systems is part of their existing workflows. Right? So if I have a recommendation system, instead of a human guessing what to do, there is a machine assisting the human guessing what to do. And as the underlying processes they have to change don't change by that much. Whereas if I do failure prediction, the process is fundamentally changed. Right? So that's another thing to think about as you're working with industrial setting, is that industries runs on processes. Right? If you want to do transformation, you have to transform the processes. The smaller the change you have to make to a process, more easy it is for them to digest. The bigger change you promote for a process, more difficult it is them to adopt those changes, because it makes all kinds of downstream and upstream effects. So that's sort of another lesson to sort of think about as you think about industrial AI. I think everyone is familiar with this. The interesting thing here is not, I just have this figure, but we've been doing this now for welding defects. And our customer gave us, I think, 30 images of defects. Right? So here we have started using things around transfer learning, as someone mentioned that earlier. And we learned from surface cracks. The idea is that when a road surface crack, the crack is very similar, say, to a crack in a weld, but the domain is very different. So things around domain adaptation are very helpful because there are publicly available surface crack data sets. And then we use that for welding, not for this one. This is an example. But my point is, computer vision is one area where industrial applications are a lot in number. And I think one thing that we'll see use of is domains where there is a lot of data, and we'll try to adopt those models for domains where we don't have enough data. Typically, industrial domains, specific problems will never have enough data. I think that's what Christopher said earlier in the very first meeting. This is my favorite problem, and it's a very simple problem. The idea was we do all kinds of maintenance activities, right? Every industry does that. So when I first came to this country, I bought a car. They said change oil every 3,000 miles. It turns out it was a scam, right? No one needs to change oil at 3,000 miles, right? How do I do that, right? So if I can do a statistical test to see whether there is a difference before and after, and then I can begin to evaluate whether my maintenance actions are helpful or not. And then you can do all sorts of downstream things around whether a practice is useful or not, whether a particular vendor is useful or not, and so on and so forth. This one is also very interesting. So this is from a steel mill. And some of them have obfuscated because I can't talk to the customer and so on and so forth. So in steel rolling mill, there's an operator. And an operator has 2 joysticks and 2 pedals. So they sit on a seat. And so when it goes through one round, they have to flip it. And so it goes back again, flip it again till you get the right level of thickness. It turns out that the way operators do this has an impact on the quality of the steel. The idea was here, and this is for a union shop, so you can't instrument the operator, right? That's not allowed. So you have to work with derivative data. So here we looked at the operational data itself and then tried to relate that to an operator to see which operator, under what circumstances, does a better job than the others. I think everyone knows reinforcement learning. I had to mention that because it will sound intelligent. And so we do this for manufacturing, scheduling manufacturing, similarly mining scheduling, using reinforcement learning to do that. And I think this is one area for very large mines where it might be useful to use reinforcement learning. It's still sort of an open sort of question. For smaller mines, you can have, human can still beat machine learning. But for a larger mine, maybe with more than 100 trucks, you will need a much more sophisticated result. I will skip this slide. This image is missing. This is PDF conversion fault, not my fault. But this problem is also very interesting, and this is sort of an open problem that I want to state here. So the idea here is that I have a property I'm looking for, and I have a lot of data, and what I want to find is a region in which this property is maximized. So I'm not trying to find the maxima or a minima. I'm trying to find a region in which it is maxima. And my region cannot be very narrow. Because what I want to do is give my operators, say, if you stay in this region, then you will do well. So if you give them very narrow region, they'll find it very difficult to stay in the region, right? So I want to give them big enough region so they can do well, but at the same time, my KPI should be high in that region. So this is sort of a very interesting problem, and I think a corollary exists in machine learning. In machine learning, traditionally, we have always tried to maximize accuracy, right? So I have a whole data set, and what is the model that gives me the highest accuracy? The right problem for industry is actually different. So in the industry, can I say, if in this region, I am very confident, and for the rest of the region, I will not say anything at all. So if you're able to build a system like that, it'll be much more useful. Because then, from an industrial context, people using your model will be confident that as long as my input is in this region, the machine learning will not make a mistake. For everything outside the region, there is humans. Right? So these two are very related problems in some sense in industrial AI. So we have 3 minutes left. We don't have enough time, but I'm going to sort of try to finish this as well. So I think some of the key challenges that I have seen and learned from is around data, modeling, and operationalization. I think everyone understands the point about historical data collection processes, data collected in different operational modes. So this data is not collected with the purpose of machine learning in mind, right? There are regulatory reasons why this data is being collected, and now you're being asked to use that data to build useful models, and it's not going to be a straightforward task, right? Around modeling, we talked about heterogeneous data or multimodal models, and small data, I think you guys understand. I don't have to preach to the choir here, but we often have to work with very small data, right? And there is a need for explanatory models. And remember, you're trying to model very complex systems, right? Look, if you look at a BOM of a vehicle, of a car, right? You have tier 1, tier 2, tier 3, tier 4 suppliers, right? So you have to model such a complex equipment of components, right? How do you do that? So there is a lot of sort of these open problems, right? Handling inconsistent. So this is something we encounter in real life. So we build a model for a customer, and they rebuild the model a month later, then rebuild the model a month later, and they all had the same accuracy ballpark, but on the same example, they were giving different results because somewhat of a stochastic process, model building, right? So domain expert says your model doesn't even repeat itself, right? So there is inconsistency between models. So how do you sort of solve this? This turned out to be an interesting problem. We wrote in a Neuro IPS paper on this. It turns out if you use an ensemble of models, even deep learning models, that gives you a better control, over consistency between models. Then you can make your models much more consistent over each other. The other thing we don't think about, especially in the academic community, is operationalization of models, right? So, and for example, cost trade-offs are very important. I'll give an example of this. I think we have enough time. How to choose the right KPIs, decision-making under uncertainty, and humans in the loop. Let me give you this example. So I have multiple models, right, here around this curve, and I'm doing failure prediction. Everyone understands this problem, right? So as I make my model, say, better, so to speak, I'm able to catch more failures, but I'm going to have higher false alarms, right? So which model should I choose? If you go to a customer and say, I have F1 score, they'll kick you out of the room because that F1 score has no meaning for them. So you really have to marry your model with an operational cost. And these operational costs will change over time, right? So the way to deploy the model is to essentially have a mechanism by which you can swap in and out and models. You can build new models and have a mechanism of making dynamic decisions about which model to choose. Similarly, there are accuracy latency trade-off. I want to give you one more example. This is another real example. So earlier I talked about failure prediction for vehicles. So it turns out that they first said, let's do, give us miles to failure. So I said, okay, if I say 100 miles to failure versus 101 miles to failure, does it make a difference to you? Obviously it doesn't, right? So from an operational decision-making perspective, we agreed on making predictions in terms of buckets, right? So whether it will fail between, say, 0 to 500 miles, 500,000 miles, and so on and so forth, right? So we came up with, say, these buckets that you see in the right, whatever this side column is, okay? And I had two models with these three different F scores. Now, which model would you choose? Can someone tell me? Because I still don't know the answer. Right? So how do you choose a model? Because for each bucket, the different F scores. A model is doing better in a different bucket. Right? So these are some very hard operational problems that you have to think about when you're trying to put these models not in a research paper, but in the field. This is generalization around foundational models, which I'll skip for now, interest of time. Where we are going is solving from these individual problems, putting these systems together for maintenance optimizations, operation optimization. And the future, I think, will be connected industries where different AIs work together to make autonomous decision making. And from my perspective, I'm not really interested in the question of AGI. I want to solve these real practical problems better than humans can, right? Where there is a social benefit. So back to this question, right? So back to this question is, so AI has to be something like this with all the properties that we talked about earlier, given the challenges that we have. Okay, so that concludes my thought. Thank you very much.
Thank you, Dr. Gupta. Some very insightful thoughts on use cases that you presented, especially the ones where you talk about operations. Industrial AI is better within operations rather than strategy or control, as well as the open problem, the envelope problem. I think good food for thought. But one thing that made me feel a lot better, I'm pushing 5,000 miles on my car. So I know at least I don't need to feel so bad anymore. So thank you for that as well. So let's just open up the section for questions.
Hey, thanks for the talk. So, a couple of questions here. So, one, do you think in today, this sort of this industrial AI, these applications, are they limited by technology? Are they limited by lack of this inside knowledge? Are they limited by these closed industries? Like, how do we solve this problem of for example, right, like Hitachi is very big, right, and I'm sure it has access to a lot of bigger industries. But I feel like real revolution is going to come when you have a lot of these smaller startups running for these some of these problems in collaboration with some giants like Hitachi. Like how do you think?
I think that's very true. The last point is very true. I think a lot of innovation will come from startups. And like the work that Christopher and company are doing around knowledge first AI, stuff like that. And partnering with big companies is where very often you'll have the most fruit. In terms of what the bottlenecks are, I would say they're everywhere. I mean, all of them. Right? So there are some technical problems that we need to solve. There are issues around, and I consider incorporating domain knowledge or building models over small data or how to operationalize these models as technical challenge. Some are challenges around lack of enough bookkeeping. So for example, when I show this, or this, so mathematically I can say, okay, find the minima, right, in terms of cost. If you talk to industries, they will not be able to tell you what is the cost. So because of the current crop of leaders, now, let me rephrase that. So because collecting the data and thinking data first is not a priority, right? So there are organizational challenges, the challenges around process transformation, and the human challenges that it brings along. So I think industrial AI will be extremely transformative. It will change the way we live. I give this talk at Stanford so that I would sort of try to motivate them to join industry, but no one would, right? All of them want to work for Google. But anyway, it's my duty to try and do that. But I think it will be transformative, but we have to overcome all these hard problems.
It's great that you have just touched on not only the technical things in this line of work, but also organizational challenges, right? How to organize people, how to adapt to processes. So I have this question. As a transformation leader in the industrial field, how do you think about the ideal setup that is most productive for AI engineers and industrial engineers to work with each other? And
So, yeah, I think that's a good question. So the most success that I have found is where the business team you're working with first of all, you have to have the business, the IT, and the AI team working together very closely. That's very important. Either of these legs of the stool is missing, the stool will fall down. So you need to have the right business problem with the right support from the business. They need to tell you what is useful. You need to have IT, especially customer IT, to get access to the right data. And obviously, you need AI. And I think the other important thing is the respect for each other. Very often, people with fancy degrees think they know more than the operator on the ground, but that's not always the case. These people have been running this thing, doing these things for so many years. There's so much to learn from them. That's the attitude at least I take when I go to the field. And I think so respect for the business, respect for domain experts, and these three sets of people working together is what leads to success, in my mind, yeah.
Great. We have time for one last question. Or maybe
Three buckets that AI and enterprise can follow: the control, operation, strategy, and the sweet spot is in operations. Do you guys have experience in the control and the seconds space? And if so, what problems have you faced?
So in the sub-second control space, the problem is typically around guaranteeing a certain result. So not guaranteeing certain bounds within which your system will operate. So we can't give theoretical bounds. And for several industrial systems, it's important to be able to give theoretical bounds so you can have some safety guarantees. What we end up doing, not in control, but in operations even, is when you deploy a model, you have to build guardrails around that. And that guardrails are both programmatic and human. So more important your model is, more guardrails you need around it so that it doesn't do damage. Yeah. So, but in control, it is very difficult to do that.
Thank you. Very good talk. Just a question about. You said you have a platform for a couple of years, and experts are retiring. There's a lot to learn from the operators. How do you harvest knowledge at scale, and what have been your biggest challenges with that?
So in that particular example, they have historical maintenance records in something called a VRMS system, Vehicle Repair Management System. So that was the main source of knowledge. And we work very close. So this is a large maintenance organization. At the top are something called VDAs. So these guys are sort of the superstars in the maintenance community and we work very closely with them to refine the model, to find out the corner cases and stuff. And I should tell you a story about this. So this model has now been operational for very many years. It's been very successful. So it has changed human behavior. And now it is causing problems for us. So this is something new that we faced. So earlier, the operators used to write complaints in good English and would take in time to write. And that was very useful signal to us. As they grew more dependent on the model, they become lazier and lazier and lazier. And they're putting more gibberish in. Right? So now the model is the old model, but it's getting a lot more gibberish in. Right? So how do we deal with that? So this is the first time where I think, at least in my experience, AI machine learning has changed human behavior, and now we have to adopt it to the second generation of humans, so to speak.
Hey, just a quick question here. So do you think one of the problems of this industrial AI is the specific customization required for the customers, or do you think these models or solutions are more generalizable? In your experience, what's been the...
I think we have tried to answer that question. What we realize is that once you solve a customer problem, you can abstract out the pipeline with enough knobs. And then when there's a new customer, you just need to sort of fine-tune that pipeline. This is sort of not fine-tuning from a foundation model perspective, but fine-tuning that pipeline. So that is sort of the trade-off. So 80-20 in some sense. So instead of starting from scratch every time, you're 80% there for a new customer, and you have to sort of do the last 20.
Thank you once again, Dr. Chetan Gupta. Appreciate it.
I just want to have a plug there's an industrial AI blog. So if you're interested in use cases and stories, please go check it out. There's actually a lot of fun stuff there.
Also, please remember to scan the barcodes for voting on this talk in the next 10 to 15 minutes. And we will take a quick 10-minute break and be back. We'll be splitting up into 2 sessions. One in the Sequoia room, which is Industrial AI Applications, moderated by Nanda Kishore. And